All right, greetings everyone. I hope that you are having a wonderful day and staying safe and healthy out there. Welcome to another exciting episode of Calculus with Cody. And yes, I just made that up, but I'm very proud of it. So we'll be continuing on in chapter 2 here. So we have finished section 2.2. We're moving on to section 2.3. Section 2.2, we talked about some basics of limits. Here we're going to take this to the next level and start looking at some properties, or what we call the laws of limits. Okay, so when we're doing laws of limits, there are a couple of things we need to kind of make an assumption of. So first of all, with each of these laws, we'll more or less be looking at two functions, f of x and g of x. And for these laws to apply, or for them to be true, we have to have that the limit as x approaches a particular value, or as our input approaches a particular value of both functions exists. And that's what this part up here on top says. Okay, so if we have that, then these following laws hold. So first of all, we're told that if we have the limit of the sum of those two functions, then we can break that into the limit of the first plus the limit of the second. Okay, so maybe that's fairly intuitive. You have two things being added together on the inside of the limit. You can break them apart into two separate limits being added together. Similarly, if we have a difference of the two functions like we have here, we can change that to be the limit of the first minus the limit of the second. So just break it apart that way. When we have it in this third form, where on the inside there we have a constant being multiplied by our function. And by a constant, we just mean a number. So something like 4, 5, 1/2, negative a million, negative pi, something like that. Well, you notice it works kind of like it does with logs, where that constant can be moved out to the front. So we end up with the constant times the limit of the function now. And then these next two are often a little bit surprising, and maybe not so much to you guys, but it's not often that if you multiply two things together, you can break them apart and do different things with them separately. So these next two are pretty nice. So we also have a product property. So if we have the limit of two things being multiplied together, then we can write it as the limit of the first times the limit of the second. And if we have the limit of two things being divided, then we can change that into the limit of the first divided by the limit of the second. And notice we do have to have this extra little caveat here that the limit on the bottom does not equal 0. Can we think of why that is? Oh, right, because we can't divide by 0. Could the top limit be 0? So could this limit up here, could this one be equal to 0? Yeah, I think so, right? Because 0 divided by anything is 0, so that's okay. Next we have our power law of limits, which tells us that if we have the limit of a function raised to a power, we can change that to be the limit, so find the limit first and then raise that to the power, which is a pretty nifty one. And then the last one is a fractional power. You can do this with fractional powers as long as the thing on the bottom of your fraction there is even. Now that one's a little less common. We don't use that one as much, but that is an option. Okay, so let's look at how we can use these, or how these are helpful for us. So here on this slide, notice that we have two different functions. We have g of x here on the left, f of x here on the right. And we're asked to evaluate some different limits down there using each of these graphs. So for the first one, we have the limit as x approaches -2 of f of x. So we're looking on the graph of f of x over here on the right, looking at what happens as we go towards -2 on both the left, or sorry, that was the right and the left. And it looks like regardless of which direction we come from, the outputs there are approaching +2 would be our limit there. And that's also helpful to see. If you notice, the graph just passes right through that point. So there's not like there's a hole on one side or the graph is broken or anything. Similarly, when we look for the limit as x approaches -2 of g of x, we go over to the left graph, look at what happens as we come from the left towards it, from the right. And in both cases, it looks like it's approaching this corner here. Even though there's that corner, it's approaching the same thing from each side. So we see the outputs there are approaching -5. Okay. All right, looking at number 3 now, the limit as x approaches -2 of f of x plus g of x. So this matches one of our limit laws now. So notice that, again, we have the limits of two things being added. So based on what we saw in that limit laws document, we can rewrite this as the limit as x approaches -2 of the first function, so of f of x, plus the limit as x approaches -2 of the second function, g of x. And hopefully now that we've done that, you see that these both match the first two problems we did, right? So here we had the limit as x approaches -2 of f of x. Here we have the limit as x approaches -2 of g of x. So let's match these here, so we can just make substitutions for each of those. So instead of writing limit of f of x, we can write what that is equal to, which is 2, plus the limit of the second thing. So as x approaches -2 of g of x, well, that was -5. So we're looking at 2 plus -5, which is -3. So our limit here as x approaches -2 of f of x plus g of x is -3. All right, let's look at the ones down below. So here we have the limit as x approaches -2 of 6 times f of x minus g of x. So I know there's that 6 in there, but I also see inside the limit there that I have two functions being subtracted. So using my limit laws, I can break that apart into the limit as x approaches -2 of 6 times f of x, so leaving that group together, minus the limit as x approaches -2 of g of x. Okay. And then before we start plugging values back in here, notice that we have that 6 there, that constant, inside of the function with the f of x. And if you remember, our limit laws told us we could take that and actually move it out to the front. So this would become then 6 times the limit as x approaches -2 of f of x, still minus the limit as x approaches -2 of g of x. And now we can make substitutions for the limit of the f of x and the limit for the g of x. And I'm sorry, this is getting a little bit sloppy. But what we'll end up getting then is 6 times the limit for the f of x, which was 2, minus the limit for the g of x, which was -5. So this will become 12 plus 5, which gives us then 17. So that one there is 17. All right, I'm going to clear out my drawings just to get a more clear view here. Let's look at number 5 now. So we have the limit as x approaches 1 of f of x divided by g of x now. So again, thinking to our limit laws, we saw that when we have the limit of two things being divided, we can write that as the limit of the top thing okay, let me try that again. So we do the limit of the top thing, so f of x divided by the limit of the bottom thing. I apologize, I'm not writing out the x approaching 1 because stylus is not cooperating. And then basically what we do then is look at the limit as x approaches 1 of each separately now. So if you look at the function f of x as x approaches 1, well, again, the graph needs to pass right through that point there. So we end up with 1 there on the top over for the limit as x approaches 1 of g of x. Again, it passes straight through there, so it looks like that also happens at 1. So here we end up with just 1 as our answer. Okay. And then for the last one, notice now we have stuff being multiplied together. So we'll have to use one of our product laws here, or the product law. So we'd break this now into the limit as x approaches -3 of 2 times f of x times the limit as x approaches -3 of g of x. Okay. And then notice in that first limit there, we have the constant inside with the function, so we can move that to the outside. And so this would become, and I know I ran myself out of room here, I'll have to write it up here. So this will become 2 times the limit of f of x times the limit of g of x. And here we're doing as x approaches -3 for both. So looking on the graph for f, where it approaches -3, it looks like that's right here. It's getting closer and closer to -5. So we'll have 2 times -5 times for g of x. As we approach -3, looks like we're getting closer and closer to 1. So we'd have 2 times -5 times 1, which is -10. So that would be the answer for the sixth one there. Isn't this stuff fun? Yeah, I'm enjoying it. All right, let's look at this example. So now we're going to look at some one-sided limits. And recall that when we first learned about limits, we found that in order for the limit of a particular function to exist at a certain point, the limit from both the left and the right have to be the same, right? So let's look at what happens here. So first on this first one, we have the limit as x approaches -1 from the positive side or the right-hand side. And we can again break this apart because we have stuff being multiplied here, right, on the inside. And notice there's a constant multiplied by 2 functions. Whoops, excuse me. And so kind of skip some steps here, but thinking about what we did on the last one, hopefully you would believe me that this becomes 2 times the limit as x approaches -1 from the right-hand side of f of x times the limit as x approaches -1 from the left-hand side of f of x, or sorry, of g of x. Okay, so let's look at what each of those values are. So for the function f approaching from the right-hand side towards -1, we see that that's this piece right here. It looks like the outputs are getting closer and closer to 1, right? So for that one, we get 2 times 1. And then for g of x, as we approach from the right-hand side for -1, it looks like the outputs there are getting closer and closer to -2. So I have 2 times 1 times -2, which would give us -4. So we know this first one here is -4, and I'm going to clear out my drawings. So this here will be -4. Okay. And then looking at the next one, it's going to break apart similarly, right? So we'll have 2 times the limit sorry. So we'd have 2 times the limit of f of x times the limit of g of x. Okay, and of course these are both now as x approaches -1 from the left-hand side now, and I apologize, this is really sloppy. Okay, so let's look at what happens with each of these functions in this case. So if we're approaching -1 now from the left-hand side in f, we see we're actually approaching a different value. So here we're getting closer and closer to 3. So this one would be 2 times 3 times, and the function g when we approach -1 from the left-hand side, looks like we still get closer and closer to -2. So if 2 times 3 times -2, which gives us -12. And notice in this case, the limit we got from approaching from the right-hand side is different from the limit we got from approaching from the left-hand side. So what do you suppose that tells us about the general limit here, about approaching -1? You guys are right. In this case, we're going to have that it does not exist because it's different from both the left-hand side and the right-hand side. All right. Moving right along then. A couple of extra limit laws we want to have. So first of all, we have the limit as x approaches a of a constant. So that's what this c means right here, is a constant. Okay, so it just equals that constant there for any constant number. And let's think about why that is. If we're on a graph and we have a constant function, what does the graph of that look like? Well, it's a horizontal line where at every point, right, the output is the same value. So it doesn't matter what input value you approach, you're always getting closer and closer to the same output value, right? So that's why we have the limit of a constant is just a constant. For number 9, we have that the limit as x approaches a of the function just x, or just the input variable, equals that value a. So can we think about why would that be true? Well, if we think again about our functions and what they look like, here we're told that the function is the function just x, which if you remember from pre-calc 1, that function is just a diagonal line going through the origin. And for each input, like say if I input 2, my output is the exact same thing, right? If I input 2, I get an output of 2. If I input 3, I get an output of 3. Input of -1 and output of -1. So as I approach any particular value, which would be like the value a here, the output I'm getting closer and closer to is that same number. So that's why we have the a here. And this last one, the direct substitution property, says that if the function f is a polynomial or a rational function, and I'll actually take this a little further, it's really, this works for any function. If the value a is in the domain of the function, so the number that we're getting closer and closer to here is in the domain of the function, then we can find the limit by just plugging it into that value a into the function, which if you think about what we just said for the function f of x equals x, hopefully that makes sense why that works. All right, so let's use these properties to do a few more problems here. So the first one there, we have that the limit as x approaches 2 of 5 is what we're trying to find. And notice that 5 here is a constant. That value 5 is a constant. So we're told that if we have the limit of a constant, the answer is just always that constant. So that one's fairly straightforward. We just get 5. When we look at the limit as x approaches 1 of 3 plus x. Well, this is one of those ones where we can look and say, is the number we're approaching, so this 1 right here, is that in the domain of this function 3 plus x? And I believe if we think about it, the answer is yes, it is. So we could just plug it in there to find the limit. So we could just do 3 plus 1. So plug in that value for 1, which just will give us 4. So the limit there will just be 4. Okay. Now let's look at this third one. So in this third one, We have a function being divided by another function. And we could break this apart that way and then try to do some sort of direct substitution, since this is in the value 5 is in the domain of both functions. So I could break this into the limit of the top function, so that x squared minus 6x plus 5 divided by the limit of x minus 5. But notice, so x is in the domain of both of those functions separately, but if I plug it into the bottom one, what happens? You guys are right, we end up with 0 down there, and that's not allowed. We can't divide by 0, right? So we have to use some other approach here. So what do you suppose that approach might be? Oh, yeah, right. The top function can factor, right? So let's see what happens if we do that. So we make this now the limit. And we should include the x approaching 5. Okay, of that top thing, which if I factor that out, I believe that will become x minus 5 times x minus 1 divided by, we still have the x minus 5 on the bottom. And notice once we do that, we have x minus 5 on the top, x minus 5 on the bottom. They can cancel. So our limit will now become the limit as x approaches 5 of just x minus 1, which we know 5 is in the domain of that function, so we can just plug it in, and we'll end up with 4 minus 1, which will just give us 3. So that limit for number 3 is just equal to 3. All right. So I'm going to leave it there for now. Those bottom 3 problems, number 4, 5, and 6, are going to be part of your classwork. Thank you for watching.